This problem is the second part of the gas injection problem, but in a deformable porous media. This is an hydromechanical problem. And now I'm going to introduce the additional information so the hydromechanical analysis can be performed. First of all, we're going to redefine the problem data. So go to Data, Problem Data, Problem Data. In the tab Equation Solved, we need to check the box of the mechanical equation. This is a stress equilibrium. And now go to the Solution Strategy tab, and we are going to introduce new tolerances related to the mechanical problem we have just added. So enter 1 exponential minus 6 in the max ups displacement, 1 exponential minus 10 in max null bulk forces, and 1 exponential minus 1 in displacement ether core. Also type 1 exponential minus 6 in the max ups PG, click accept and close the problem data window. Now we're going to define the material. A constitutive law to define the stress-strain relationship has to be defined. So go to Data, Materials. By simplicity, a linear elasticity law has been selected. Now I'm going to introduce the parameters. You can skip this part. After introducing the new parameters, you don't need to assign the material again because it's already assigned to the surface of the problem, but you need to save the changes made to the material. So now close the materials window and let's define the mechanical boundary conditions and an initial stress state. Go to Data, Conditions. We're going to define a null displacement at the boundaries. So go to the line icon, select force displacement BC from the drop-down menu and boundary stress from the forces drop-down menu. Now enter 0 on the x direction prescribed field and 1 on the y direction prescribed field, and assign this condition to the line 1. Click Finish. Now the same value 0 in the x direction prescribed field and minus 1 in the y direction prescribed field, and assign this condition to the line 3. Now enter the value 1 in the x direction prescribed field and 0 on the y direction prescribed field, and assign this condition over the lines 6, 8, 10 and 9. This is all the left boundary. Click Finish or Escape. And now the last one is minus 1 in the x direction prescribed field and 0 on the y direction prescribed field, and assign this condition over the right boundary. These are the lines 11, 13, 15 and 16. Now you can visualize the conditions assigned using the option Draw, Force Displacement BC. And note that we use the minus 1 value, so the icon is drawn on the exterior of some lines. Now select the surface icon And let's assign the initial stresses. So choose from the drop down menu initial stress and introduce minus 0.1 in the X, Y and Z stress fields. Now assign this condition over the surface, and once assigned, click finish. Now you can check all the conditions assigned using the entities all conditions, and all conditions summarized will appear. If everything is okay, we can continue and process the problem. But first we need to generate again the mesh, so go to Mesh, Generate Mesh, click Yes to delete the old mesh, and click OK to generate the new one with the previous values inserted in the previous problem. So now we can continue, go to Calculate, and wait till the process is finished. Once the process is finished, you can access the post-process interface using the post-process button, or access later. If you go to Calculate View Process Info, you can check all the variables of the simulation in case an error occurred or something happened. Here you can verify what's wrong. In this case everything's okay, so I'm just showing you. So now click Close and let's access the post-process interface. Now go to Window, View Results. To analyze the results of the problem, select Contour Field from the View drop-down menu. And here we can analyze the same variables as before. These are the distribution of the gas pressure. We can use the animate function to visualize the change over the time. This is a hydromechanical problem, and well, the degree of saturation, porosity, displacements. You can view the result you are interested in. It's very useful, this animate function. You don't have to change every time step. I will continue displaying some results now. Now we're going to analyze the evolution in time of some variables in 3 specific points. These points are the central point of injection, a point in the middle of the sample, and a point very close to the central point of the output flow, the same 3 points as the previous simulation. So we're going to analyze the gas pressure, liquid pressure, degree of saturation, and also the X displacements. So go to the graph icon, select point evolution, and let's start with the gas pressure. Select the 3 points mentioned. You can enter the coordinates or select the points in the graph area. Here you can change some options of the graph, in this case the logarithmic scale I'm using. And here we have the gas pressure, the time evolution in 3 different points. So here we can see that due to the compressibility of the medium, the gas and we will see that the liquid pressure too are reduced, in particular at the point P1. So clear the graph with the red cross, and let's do the liquid pressure graph now, just following the same steps but selecting the liquid pressure. The coordinates of the 3 points used are, for the P1 point, 0,0.06, for the P2 point is 0.015,0.06, and for the P3 point is 0.029,0.06. I just click on a near point using the coordinates and the graph area because it's easier for me, but you can introduce the coordinates using the message box. And now let's do the degree of saturation point evolution graph. Always we follow the same steps. So select the graphic icon, point evolution, the variable you are interested in, liquid saturation degree in this case, and choose the points. And while the saturation is higher in comparison with the observed in the hydraulic analysis, this is because the saturation is easier by the presence of an aperture or fracture in the medium and the compressibility assumption. Because of the fracture aperture, permeability increases and a preferential path of gas flow is allowed. And now let's do the x displacements point evolution graphs using the same points, and always the same procedure. Select the graph icon, point evolution, displacements, x displacement for this graph. Select the 3 points. And escape and you will get the graph. You can modify the graph options from the options tab, like the axis scale, if you want a logarithmic axis or not, and a lot of other options. And you can delete the current graphics using the red cross icon. I always clear the graphs in order to avoid superposition with the new ones. But if you want to keep all the graphs separated, you only need to create a new graph set. So this is the end of this tutorial. To exit the program, go to Files, Quit.